Hello, this is Professor White. Today we will cover the theory behind equations. I'm going to go over a couple of theorems and kind of review them. Please watch the previous video along with this one. So I really recommend that you watch the previous video in College Algebra List before you do this one. Okay, so we are going to look at how we can look at a polynomial, an equation, and then it says, oh, there are that many possible roots. And root theorem that comes with that. Conjugate pairs theorem. So if you have conjugate imaginary numbers, they come complex numbers, they come in pairs, and so that's the theorem. And then Descartes' rule of signs that really narrows it down. And theorem of balance that you can use and to rule out a couple of things in terms of your possible lists of roots, and you can narrow it down using that theorem on bounds. So let's get started. Okay, now let's look at the Fungal Theorem of algebra. Again, I did that in the previous video. Oops. All right. What did the Fungal Theorem of algebra say? If you have an nth degree polynomial, it will at least have one root, and your n being bigger than or equal to 1. And then that one root will be in the complex domain. That means it can be a real number, it can be an imaginary number, it can be a complex number. So it can be a 2, it can be a 2i, it can be 2 plus 2i. Alright, what is the next one? We did that in the previous video. Linear factors theorem. How does that work? What did we talk about? Again, you have a p of n, and you have a leading coefficient of a n. Let's say this is like this. A n x to the n, it goes all the way down to a1 x plus a0. Alright, and n is not 0. Okay, good. So I can write this, linear factors theorem says, I can write this as my leading coefficient, x minus the first root, x minus the second root. And first and second root can be the same. They can be complex. They can be imaginary. It can be anything, okay? And then you can actually write them as a product of linear factors. That's called linear factors theorem. Okay. Now, the rational roots theorem. What was that about? It's in the previous video as well. Remember, given p n of x, and the roots are going to be a ratio of p over q. And what is p? These are factors, possible factors of your constant term, and q is the factors of your leading term. We did that. Now let's go and kind of narrow it down, because remember in the previous video I was just looking at the possible roots and everything, but the problem was I have too many of them. How can I narrow it down? How can I say certain things, okay? So let's go and try to find that. That will be upper and lower bound theorem. This is how you find the upper and lower bounds for roots. You take your Pn, and you suspect that x minus c is a factor. Just simply divide it. Alright, do a synthetic division. And the last row, if it is all positive, and for this to work, put your Pn of x as your leading coefficient as positive, okay? So if you get all possible terms, positive terms in the third row when you do your synthetic division, that means that C is an upper bound for your root. Very, very handy. Okay? The second thing, again, I take Pn of x, I suspect x minus c is a factor, and I just go ahead and divide it. And again, have your an positive. Now this time on your third row, you're going to have alternating terms. So that means is c will be the lower bound for your polynomial. So I'll give you an example so that you can see how this works. Okay, let's have this example. Let's say somebody says, what are the upper and lower bounds for the terms, for the roots of this polynomial? Now remember, usually people don't like fractional constants. So I think it's a good idea, since you have a 0 on the side and you're looking for roots, just multiply everything by 4. If it wasn't all 4, what would make sense to multiply everything by? The lowest common multiple. Just take your fractions, look at the lowest common multiple, multiply the whole thing by that. Now when you do this, you'll get x fourth minus x cubed plus 17. 4 times 4, 16. 4 times 5, 20. Okay? Now, I'm going to kind of look at that, and let's find the rational roots theorem says, okay, get your candidates. P over Q. What are those? You're going to have a 20, you're going to have a 1. So for the Q, you have only plus minus 1. For 20, you're going to have plus minus 20. You're going to have plus minus 1. You're going to have 10 times 2, so plus minus 10. How about 5 times 4? Plus minus 5. Plus minus 4 times 5. Okay, plus minus 2 and plus minus 1. If you look at this and you take this and then you divide it by plus minus 1, where are you going to end up? We are going to end up with a zillion candidates. All right, so what you should do, you should actually look at some possible, first of all, let's look at that. Let's go and check for positive roots first. So what was your first non-zero positive root? It was, the candidate was 1. So go do the synthetic division, 1. So I put 1, negative 3, remember these are the coefficients, 17, 16, and 20, and do the synthetic division. You're going to get 1 times 1, 1, negative 2, 2 times 1, negative 2, 15, 1 times 15, 31, 31, 51. Now I look at the last row. What does that say? Okay, first of all, this is not 0, so it's not a root. But is it a bound? How does the bound work? It's supposed to be all positive, or it's supposed to be alternating. And that ain't it. So 1 is not a bound for it. So let's try the next positive root, 2. You do the same thing. 1, negative 3, 17, 16, 20. And do your thing. You're going to have 1. So 1 times 2, negative 1, negative 2, 15, 30, 46, and then 2 times 46 plus 2, 92, so 112. Again, this is not a root, and this is not either all positive or alternating nicely, so that ain't it either. So let's try 4. So I try 4, 1, negative 1, 15. Oh, sorry. I'm looking at the wrong thing. 1, you have negative 1, 1, negative 3, I'm trying to shortcut and getting in trouble. Negative 3, 17, 16, 20, here's my polynomial. And I'm going to divide by through 1, okay, negative 3 plus 1, okay, 1 times 4, so that's 21. That is going to give me 84. And you add 100 and 400, 420. Or something happened here. Some happened that didn't happen with 1 and 2. What happened? I got all positive. What does the lower upper bound theorem says? It says 4 is an upper bound. What does that do? Go back to your list of possibles. Okay? Look at my list of possibles. That takes out 20, the pluses. That will take out the 10. That will take out the 5. That's it. So I reduced those things already. So if I go and look at the negatives, and then if I find something, then I'm going to even narrow it down more. Okay? So I know that my positive roots can only be 1. What else I have? I have 1. I have 2. That's it. Okay? 4 is the upper bound. It cannot be 4. And it's not 4 because when I hit 4, it's no good. It's not a root. So I have 1 and 2. And that narrowed it down really, really nicely. All right. Now let's look at negative roots. Okay, so I'm going to try negative 1. And let's do the synthetic division again. 1, negative 3, 17, 16, 20. And the same thing, I do my synthetic division. And I do 5, 25. So negative 1 is not a root. However, look what happened. I got an alternating situation. What does that mean? Negative 1 is the lower bound. So my roots have to be between negative 1 and 4. And that really, really limited it. So this lower upper bound thing is really, really handy to narrow down your candidates. Okay, so what is the next thing I can do? The other one is Root Theorem. We're going to use all these theorems together. So let's say I have a nth degree polynomial and I'm looking for its roots. Okay? Counting multiplicity, you can have at most n roots. It has to match this guy. For example, if I have x minus 2 cube and x fourth minus 9, what's the degree of my polynomial? You have a 4 and a 3, so my polynomial is 7. So that means I have at most 7 roots. That's the Root theorem. And that's really good. If you go and find 9 roots, you're doing something wrong. Okay, how about the next one? Conjugate pairs theorem. How's that work? So if you have a root and you found it, a plus bi, as a root when you're looking for it, then you are going to have, they come in pairs, a minus the conjugate counterpart of it as a root as well. Okay? For example, we did this example before in some of the videos. For example, I got x squared minus 4x plus 5 equals 0. And we went and we found out that 2 plus or minus I is a pair of complex roots for that polynomial. Okay? So it came in pairs. So that really, really will help. Okay. Now, for example, where else can you use this? For example, it may be, here's another example. you may have 2x to the fourth minus 3x cubed plus 12x squared plus 22x minus 60 equals 0. So what does that tell me? I will have at most 4 roots. Okay? Let's say they gave me one of them. 1 plus 3i is a root. It's given. They gave me that information. Then the conjugate pair theorem says, so will be 1 minus 3i. Well, how can I use this? Just multiply them out. So you can have, so since the first one is a root, 1 plus 3i, the linear factor theorem says you can actually do this and FOIL it out. When you FOIL it out, I will actually write you the end product. You can check it. This is what you get. Okay, so since linear factor theorem says, okay, that means I can look at this and find the other 2 roots. I don't know what they are. Well, how can I find the other 2 roots? What you can do, you can take your polynomial and divide by the 2 roots you know, which was x squared minus 2x plus 10. When you do this with synthetic division, this is what you're going to get. 2x squared plus x minus 6. So I can go, and this is a quadratic. I can go and I can find the roots of that thing. And to find the roots of that quadratic is very, very easy. You can actually use factoring. 2x minus 3. X plus 2. Well, that will give me the other 2 roots, 3 halves and negative 2. You see how fast we got there. What you can say, okay, well, this whole thing can be factored as x minus 3 halves times x plus 2 times the complex roots, x minus 1 plus 3i times x minus 1 minus 3i. And when I plug in any of these values, I will get 0, which means I have 4 actually roots. Okay, all right. Now, the other one that's just put it all together is Descartes' rule of signs, and that is very, very handy tool. And it is named after the mathematician who found this pattern. Okay, so this is the last one. You have to kind of pull all these theorems together. Let's say I have Pn of x equals 0. I have all the things. Okay, now, before you even get started, you can actually tell. Remember, I get all these with the, with the possible roots, candidates, and all this. I end up with a bunch of things. Maybe I should just go ahead and eliminate those from the get-go, at the beginning. And this is how you can do it. Number of positive roots. Okay? You're going to see that by looking at your polynomial, a number of variations in P of x, or is less than that by an even number. What does that mean? I'll just tell you in a minute with an example. Number of negative roots, on the other hand, you're going to look at the number of variations again. Number of variations in P. All right? sorry, it's not p of negative x in the same way, or is less than that by an even number. What does that mean? I think the best thing is to do an example so you can see it. So let's look at one. X cubed plus 8x plus 5. Okay? Now I'm looking at number of positive roots. Okay? Is it possible? I need to have a variation. In other words, plus, minus, something like that. And I don't have any. Number of positive roots is 0. I don't see any. To look at the number of negative roots, what do I look at? I look at p of negative x. When you do that, you're going to get negative x cubed, negative 8x, plus 5. How many variations? How many times does this polynomial change sign? One time. So number of negative roots is going to be 1. Or less than that by an even number. If I put an even number, the smallest even number I can think of is 2. 1 minus 2 is not going to work, so I need the positive number. So it's going to be 1 negative real root. Okay? Well, the nth degree theorem says you have to have 3. So where will the other 2 come from? If I don't have any negative roots, I don't have any other positive real roots, what is possible? That has to be 2 imaginary ones or complex ones. So 1 will be a real one, and then 2 will be imaginary or complex. Okay, good. And they come in pairs, and it's an even number. I got it. All right? So Descartes actually really helps me figuring those out. So let's look at this one. X to the 4th plus, let me put that 0 so you can see it, x cubed plus 3x squared minus 7x minus 5. Let's look at the possible roots. How many times does this thing changes? Now, first of all, let's find out how many roots I'm going to have. This is the 4th degree. Nth degree theorem says you're going to have at most 4 roots. Some of them can be repeated, but it's going to be 4 total. Okay, so let's look at the number of positive roots. I just simply look at this thing, p of x. How many times does this one change its sign? It changes sign right here, right? So positive roots is going to be 1. Okay, well, let's look at the negative roots. Negative roots, what am I supposed to look at? I'm supposed to look at p of negative x. Put that negative, and then let's get it. I'm going to get x to the 4th minus x cubed plus 3x squared. And when you put a negative, you're going to get plus 7x minus 5. How many times is this changing? Okay? All right, so let's look at that. Okay, I got, here's one, and here's another one, and here's another one. Okay, so I had, remember, 1 positive root, and then I have 3 negative roots. Okay, what does that mean? That means I will have 3 negative roots, or I will have 2 less than that 1 negative root. Does that make sense? Okay, so I have, let's see if I copied this right, plus 3x squared minus 7x. Okay, so So I'm going to have one positive root and three negative roots. If I have one negative root and one positive root, where will the other one will come from? It's going to have to come from the two complex roots. Does that make sense? You don't see all that stuff. Okay? So what did I look at? I just looked at the possibilities and things like this, and then so that I can have maybe, you know, you cannot just go and pick anything else and kind of like figure things out. It's just that's pretty much it. You're going to have one positive root, three negative roots, or you're going to have one positive root, one negative root, and then two complex roots. There's no other way. Okay, so let's look at another example. Let's insert some pages here. All right. Let's say I'm looking at P of x equals x cubed minus x squared plus 3x plus 2. And let's look at P of negative x. That's going to give me negative x cubed, negative x squared minus 3x plus 2. Okay. Now, how many changes do I get? Here's one. Okay. And here's another one. So you have two positive roots. How about here? You're going to only have one. Okay? So what are the possibilities? If I have two positive roots and then one negative root, that's totally possible. Okay? Now let's take the 2 away from the 2, so that means 0 positive roots. You'll still have one negative root, but the problem is I need to get to 3, so that means I'm going to have two complex roots. All right? So you can actually decide and you can try different things. So how do we put all this stuff together in an example? And that is actually pretty good, looking at the whole picture. So let's do an example. 9x cubed minus 15x squared plus 11x minus 5. Let's look at the positive roots first. How many times does this change sign? Here's 1, here's 2, here's 3. So 3 positive roots. Okay? Or take 2 away, 1 positive root. If I have, okay, so let's look at the negative roots now. I put P of negative x, so I'm going to get negative x cubed minus 15x squared, negative and negative. Guess what? That tells me that for negative roots, I don't have any. None. Okay, so I have either 3 positive roots or 1 positive root. If I have a 1 positive root, I have to have 2 complex. These are the only possibilities. So when I come up with my list of roots, I can just take out all the negative roots from the bat. Okay, so let's look at the rational roots with the rational root theorem. How does that work? The rational roots, I'm supposed to look at negative 5, so that will give me plus minus 5 and plus minus 1. When I look at 9, that gives me the other ones, plus minus 9, plus minus 1, and plus minus 3. Okay? Now, since I have no negative roots, I don't have to try the negative roots. Let's try the positive roots. Since I may have 3 of them, try the smallest one. What is the smallest positive? It's positive 1. So what is the fastest way to check that? Just divide with synthetic division. 9 minus 15, 11, negative 5. When you do that, you're going to get 9, negative 6, 5, and 0. That means x equals 1 is a root. Now what can you do? What that means is that I took my P3 divided by x minus 1, and I got this, 9x squared minus 6x plus 5. What does that mean? This is a quadratic. I can solve that. I can look at this, and I can go and do this thing. And let's do it. Quadratic formula. Oops. I'm going to get 6 plus or minus b squared minus 4ac, so which is 36,495 divided by 2 times 9. When you clean that up, you're going to get 1/3 plus or minus 2/3 I. So what did I find out? I found out that x equals 1, as expected, is one positive root, and I got two complex ones, which is 1 plus or minus 2i over 3. And remember, I knew all that at the beginning of the problem. All right? So you can use all these different theorems to nail down. Actually, graphing calculators make all this redundant, but it is a handy tool. You can look at it, let's say you're on an island by yourself and there's nothing around you. You can do these problems in your head.